Okay, thank you for having me. So I've seen a lot of really interesting GR talks where everyone is thinking very big, and today I want you to think very small. So who am I? My name is Alden Waters. I'm a visitor to Alexander Strohmeyer. Most of the work you'll hear today is joint work with Alexander, who's not here, and we'll both be migrating south for the fabulous weather that Hanover has to offer us later in the year. Okay. So for those of you who largely do GR, we'll have kind of a nice introduction to what it is that we are doing. You won't see a lot of proofs today, but you're free to peruse the archive should you be disappointed on that matter. All right, so brief outline of the talk. I'll introduce the mathematical objects that we're interested in studying. I'll show you a little bit of layer potential theory for the Helmholtz equation. I'll show you how that ties into layer potential theory for Maxwell's equations. We'll express Maxwell resolvents in terms of layer potentials, whatever those are to you at this point in time in the talk. And we'll discuss why this is important. So keep in mind, I want you to think about very tiny things today. So I want you to think about the Casimir effect, which is a microscopic force in between two objects. Okay? So we start off with some collection of open, bounded Lipschitz domains in R3. We'll just focus on R3 for today, so everybody can visualize what's going on. The finitely many connected components are considered little Lipschitz obstacles in space. We can take as many of them as we want, as long as they're finite. We assume that they're disjoint just for simplicity's sake. M, for the purposes of today's lecture and pretty much in all of our papers, is the exterior domain. Omega is the interior domain, and it has a boundary. Okay? We also have an everywhere defined unit normal. Okay? Everybody likes a good picture. So this is our collection of Lipschitz obstacles. Before, in earlier papers, we were dealing with smooth obstacles. Lipschitz obstacles are a bit more difficult, but they're also more realistic, right? Everybody who does physics, they take one plate and another plate, which are two Lipschitz domains, and they move them together or they move them apart to study the Casimir effect. And the only time you're going to get something smooth is you have two balls or two ellipsoids, and that's not always the case. Later on in the talk, we'll also we'll simplify, and we'll just take one Lipschitz obstacle and another one and see what happens there, okay? But really, we can take any configuration, which is nice. So the first thing I want to convey to you is that the Casimir effect is a byproduct of a complicated system of equations called Maxwell's equations. So let's take a very simple version of this. We're in R3. We want to study Maxwell's equations in time harmonic form. So we start with separation of variables, e to the I lambda t. And then what happens is that we arrive at this system of equations. You already see that we have some mixing. We have nu cross E. E is some kind of vector field. And nu inner product at H. So these types of mixed boundary conditions. And so this coupled system, when the vector field E is divergence free, reduces to something that looks like this. And E has to be kept divergence free. Remember, we still have our obstacle here, so it starts to get a little bit tricky. But you would think that this would result in the spectral theory of Laplacian on divergence-free vector fields. You think, this looks like the Helmholtz equation. Right? Easy. No, not so much. That's what I thought the first time I saw it. So Let's start off studying some spaces for Maxwell. Keep in mind I come in the background in harmonic analysis, so I like little technical things. So we start off with this big capital H space. So this means that F is a vector field which is in L2, and the curl of F is also in L2. This one, the little d's and the little c's are for the whole manifold, whereas the big d's and the big c's are on the boundary, okay? So there's a difference between surface divergence and divergence in the whole space. That's a bit confusing at first. So, all right, we have these technical definitions. We also have this special space, which is L2 tangential. So these are vector fields on the boundary, such that the normal component is 0 everywhere on the boundary. And we have these two funny spaces here. And so what I want you to think of, if you've never seen this before, the way that helped me think about it is that we're replacing this H1M space when we deal with Lipschitz domains with the first space, or the first two spaces. And the last two spaces, if you're looking at like the Dirichlet-Neumann map or the trace, replace this notion of the fractional spaces on the boundary. Okay, so if you're going to study the boundary value problem, you have to have some version of these spaces to help you if you're with a Lipschitz domain. All right. So the important part about the Lipschitz domains is that your Sobolev spaces are only defined for s less than or equal to 1, right? There's no invariance under Lipschitz mapping unless you don't have this low regularity space. Okay, so this is why these spaces look like a little bit strange, that they have some regularity in some directions and some in another. So even just to start off with, so let's even go back to our earlier system. If we go back here, and let's just say that we give f is 0, and we want also that the restriction of E on the boundary is 0. So you can already see translating between people who use relative boundary conditions, which means that they say that the surface divergence is 0, and people who do numerics, which is they say that U cross E is 0, takes already a little bit of work using vector calculus. So I showed this computation to see that it's a bit like, all of these computations are a bit like vector calculus on steroids. Okay? So we are really interested in a very specific case where the tangential component of E is 0, E is divergence free, and U cross E is 0. This gives relative boundary conditions. And remember, I told you that we were going to talk about the Casimir effect today. So the Casimir effect we study actually for two perfectly conducting obstacles. And these have some spectral theory representation in terms of perfectly conducting boundary conditions. And one of the major goals of our articles was also to connect this group of people doing spectral analysis using forms, and to connect them with the people who are doing numerics, and to try to see if we could find some common language. All right. So again, you have these spaces where we have certain directions have a limited regularity. We can define them, we can extend them to the Lipschitz case. And these spaces were really set out for us by Buffa and Hiptmeyer. All right. So let's skip a little bit forward. And since this is not a group of technical specialists, most people are doing GR, let's talk about layer potentials. Remember, we saw earlier that the Maxwell equation system looks temptingly like spectral theory for the Helmholtz equation, but it's not. So I didn't know anything about layer potential theory when I first started this. And so what is the basis of this idea? The Green's function in the free space for the resolvent, and so we're going to try to find a solution to a boundary value problem in a moment here, looks like this, right? And this is nice in 3 dimensions, and it's completely explicit. Once you start getting an obstacle in there, the Green's function is no longer explicit. If you're in the interior, you're in luck. You can use separation of variables, basis of eigenvalues and eigenvectors. But if you're in the exterior, you're pretty out of luck, right? There's not a good classification there. So people are smart, and integration by parts has been around for a very, very long time. So we define the single layer potential operator from this space right here, if you're Lipschitz, h to the minus 1/2 on the boundary, into h1 log, so you can define it everywhere, as this, and this is the restriction map, the dual to the restriction map, and the single layer operator is this, okay? So this is symbolic, and it relates the resolvent to some kind of kernel, but let's write it out explicitly. So people, what they do is they represent solutions to the Helmholtz equation with boundary conditions, h of x. So let's say you have some kind of domain in outer space. You have h, which is defined on the boundary. You take this kernel, so you take convolution with g of y on the surface. So x can be either inside or outside of the obstacle on the surface. And you take g of y to be this. So this is the inverse of the layer operator, the single layer operator. And this is defined by convolution with a free space Green's function. And this solves the Dirichlet problem. So if you actually take the restriction of S, which is defined everywhere, against this, you'll see that you get back actually to the h of x. Okay, so it's done symbolically, but the outer integral is totally tractable. The outer integral is over a boundary, which you usually have, and the single layer operator itself can actually be defined in terms of the exterior and interior Dirichlet to Neumann map. Right? So if everything is smooth, you can actually write down an equality for the Helmholtz equation. So if you take the imaginary part of lambda is greater than 0, you don't have any convergence issues. U restricted to the boundary is h, and you can see that U is S tilde, which is this nice kernel, applied to S lambda inverse, applied to h. S lambda inverse is the sum of the interior and exterior Dirichlet to Neumann operators. There are some nice jump relations so that you can calculate this. And this is nice because it takes a very complicated three-dimensional problem and it reduces it to something much more tractable that people doing numerical analysis, the people doing harmonic analysis can get their heads around. All right, if you take lambda to 0, what do you get? You just get the standard problem for a boundary value problem for Laplace's equation, which was actually the first thing that people studied. So I wanted you to have in the back of your head that we are studying the Casimir effect. So what is the Casimir effect? So there was a Dutch physicist, and his name was Heinrich Casimir, and he was working at Bell Labs. And he noticed that the interaction between colloidal gold particles, that they were interacting like there was a force between them, even when they weren't charged, even when nothing was there. And he hypothesized that perfectly conducting obstacles had some sort of force in between them. And he called it the Casimir effect. And of course, everybody looked at him and he said that he was totally crazy. Okay? They did an interview with him years later when people had measured this effect, and he looks into the camera with his steely blue eyes and he said, I was right. Yeah? So I'm a mathematician. If I measured this imaginary force, I probably wouldn't have told anybody, right? I never liked anything I couldn't prove. So we started off the first way, trying to get to the Casimir effect via relative trace formula using functions, right? You can think of this as like first order approximation. We kind of ignore this nu cross E, this mixing of the boundary conditions, and we use our layer potentials to try to get at this first. So for the purposes of today's exercise, we'll just take two bounded domains. Our first result was in RD. So we have the operator defined by the Dirichlet quadratic form on RD minus the boundary of both obstacles. And then there's each one of these, J is 1, 2. There's one obstacle and another obstacle separately. Okay? So we want to measure the energy from two obstacles, right? The difference in the energies. It's not the free space minus the energy of the obstacles. No, it's really the force in between the two obstacles. This one is also the free Laplacian. We define this by the functional calculus. If S is negative, then of course you have some domain issues. But we'll start with everything smooth. Remember, first order approximation. So as part of our first theorem, we say S is greater than 0, M is greater than 0, and we take this operator, which represents the Casimir effect. So it's the energy from these obstacles in between them. And we showed that it was trace class, and that the trace is given by this formula, okay? So if you're not familiar with the functional calculus at all, what's really amazing about this formula here is that this is the unique combination of these operators that is trace class. So if I take any just combination here or here or here, it's not true. Okay? So you have a problem up to the boundary, right? What are these objects? You have a free space resolvent, and then you have a resolvent with an obstacle removed. So maybe far away, you're okay. And usually when people do relative trace formula, they have some cutoff around the boundary. But you have some issues with matching up the domains right at the boundary of the obstacle, which is what you would expect if you're subtracting things off that live on different domains, right? So what's so unusual is that you can actually write down this formula like this, and that it's trace class. Yes? Normally, you would have to take some cutoffs away from the boundaries. And it's given by this formula. And what is this thing right here? So this is called the psi function. And the psi function is obtained by a Fredholm determinant. And it turns out that this is equal to log det. So this is a Fredholm determinant. Think of like a regular matrix determinant, but on steroids. And that this is the single layer operator. So this is the operator acting on the boundary. And this is composed with the direct sum of each of the two operators, one with the obstacle 1 in, one with the obstacle 2 in. Okay? This object is tractable. There's people who work on numerics who can compute this using finite element methods quickly and explicitly. And this is why we wanted this object in particular. So these operators, they're known. We prove this equality. And now we have a way of, if we were to pretend that the Casimir effect didn't have these boundary conditions, of getting at a computation for the Casimir effect. And actually, relatively recently, Professor Timo Betke and his PhD students, Shashu and Alexander, they actually did numerics that match up with the predicted value of the Casimir force using this scenario for the function case. Yes? So this actually ends up being a perturbation of the identity. So it's quite close to the identity And so this allows for, it's actually easier if you see what the Casimir energy is in terms of these previous quantities. So this is the Casimir energy to first order approximation. And this is given to us in a paper by Yanlong Fang and Alexander Strohmeyer. I'm not on this paper. And so they show that this is differentiable as a family of trace class operators, and the derivative is the Casimir force. Again, this ignores a little bit of the boundary conditions of the new cross. Okay. So I promised you that we would go back to the Maxwell system, right? You've seen that there's a relative trace formula. The trace formula works in any dimension. It's for the Dirichlet Laplacian. But the Maxwell case is a bit trickier. So there are problems forming the solutions to Maxwell's equations for these so-called zero boundary conditions or relative boundary conditions. You also have a problem about what the representation formula means at lambda equals to 0. So at lambda equals to 0, what does it even mean to be a system? Right? So Maxwell's equations, if we go back several slides here, all the way back, it's almost completely uncoupled. And if you put a 0 here, then what does it mean? Does it have any meaning at all? So most of the previous literature you'll find uses lambda not equal to 0 because h of x is equal to I curl u over minus lambda. And well, at lambda equals 0, you have a problem, right? So if we want to start defining boundary layer operators for Maxwell's equations, we start in this way, right? We start the same way that we wanted to start for the Helmholtz equation, except for to make it a divergence-free vector field. So rather than A integrated against the free space Green's function on the boundary. So this is a vector field, so we take 3 copies. And A is a vector field, so it's actually 3 copies with the free space Green's function. And then we take curl curl. So if you take divergence of curl, you're already good, right? So you're a divergence-free vector field. And so this is how people start doing layer operators for Maxwell. We wanted to try to use what was already there to develop a much more complete theory of relative traces. So the Maxwell single operator is then the tangential restriction of this. And I've thrown the definition of these spaces at you very quickly. But if you're not an expert on Lipschitz domains, just know that they're out there. They look like that so that they're well defined on the boundary and so that you're invariant under Lipschitz coordinate changes. And so much like in the previous case, if we had F being our boundary data for nu cross E, then this layer potential inverse composed with the single layer operator inverse composed with the layer potential itself gives you a way to compute the electric field. Okay? So same idea, we had single layer operator composed, single layer potential operator composed with layer potential inverse to solve the Helmholtz equation. Now we have a curl curl stuck in there and a little bit of a rotated space, but we can still solve the boundary value problem. What's nice about this is that this representation holds in the interior and in the exterior. Why do I keep talking about lambda equals to 0? And also the space div 0, which is when nu cross E is 0 on the boundary. We'll get back to that in just a second. So you can see that this operator, which we already showed, if we take 3 copies of this, then we can expand this to a vector space. So instead of going from -1/2 to 1/2, much like the Dirichlet-Neumann map, we can take 3 copies of this, and then we can also use this to start to write our layer potentials. So this is going to be good, because if you think of it this way, then the layer potential can be rewritten in the following way. And now you can really see that at lambda equals to 0, this term is 0. And if the surface divergence of A is 0, then this is 0. Okay? And this is not particularly helpful. It doesn't provide any further information. So why am I so interested in this? So these cannot be avoided. These specific issues cannot be avoided with the techniques that we're using. So we use some type of functional calculus and contour integration in the proofs. So we have to go through 0. We can avoid most of the real line, but we have to touch it somewhere. That's sort of a caveat of the functional calculus that we're using. And to get to relative boundary conditions, we also need the surface divergence to be 0. So relative boundary conditions allow us to express a lot of these things in terms of the functional calculus, because they give us self-adjoint boundary conditions. And so this is why it was very important for us to conquer these hurdles. So let's take a brief aside and talk about where this is in the literature. So there are a whole wealth of papers by Michael Taylor on layer potential theory, by Dorina Maitreya, by Marius Maitreya, also Irina Maitreya. There are 3 of them, but largely there are 2 of them who work a lot together, much like us. They do LP to LQ estimates because they are harmonic analysts, and they also reformulate their spectral theory in terms of the Hodge Laplacian. They have several books. A lot of the information about the Fredholm theory is done in C2 domains. Some of our audience members also participated in the writing of these papers. They also have things for Lipschitz domains, but the structure was not as useful for us. At the same time, a group of people who are not using high-power spectral theory, Annalisa Buffa, Ralph Hiptmeyer, Martin Kostabel, these 2 are at ETH, this person is at Rennes. They set up spaces for numerical analysis, and they set them up so what's called the boundary element method worked. And this is why they won a bunch of prizes for this, was that they were able to precisely identify these spaces and their connection to each other, so that they could use numerical analysis, and that they could actually write down electric and magnetic fields. So this book by Kirsch and Hedlisch from 2015 is great. I use this quite a lot in the writing of this paper. I've mentioned Timo Betke in the UK, who's been doing a lot of the numerics associated to this work on the Casimir effect. And further away, which we won't have time to talk about, are Gustasi, Steinman, and Lesch. We also have spectral shift formula, which relate these relative trace formulas to the spectral shift function and also to scattering matrices. Okay, but it's a finite time talk, so we won't hear about them, but they're interconnected. We have not seen that there's Lipschitz domains with lambda equal to 0 and relative boundary conditions in this selection of literature, although we use the background quite extensively. And remember, we are interested specifically in this application of developing a relative trace formula for the Casimir effect. So are there any questions? So far, everybody's learned everything that there is to know about layer potential theory in the last 10 minutes? All right. So we also do the H field. So if you look at the layer potential theory, where did it go? Here. So you can express h of x in terms of curl of E, or you can use, we call it m tilde lambda. So there's a magnetic layer potential, which is just the curl of A G lambda x. So if you get 3 curls, you actually come back to where you started from if you're divergence free. And so we do actually do the magnetic field as well in this paper. And the Casimir effect turns out to be the sum of 2 forces from the electric field and from the magnetic field. This is something that Jan Long and Alexander are still working on, although please don't ask me what the other paper says, because I was on maternity leave when it was written. I still haven't quite caught up to that. So we do both in our papers, which is an important point to notice. It's electromagnetic scattering because you have both the electric and the magnetic fields, and they're coupled to each other. Even though if you have relative boundary conditions, it really looks like just the Helmholtz equation in many cases. Thank you for the question. So now I told you that we can do arbitrary obstacles and that we can express the force, the Casimir effect, from arbitrary obstacles in terms of these layer potentials and the Fredholm determinant. So now let's start with our Lipschitz data. And we just take 2 obstacles. Yes? So if we just take 2 obstacles, this thing right here, much like we had before, is the direct sum of the single layer potential acting on one object and the single layer potential. Sorry, I get the words layer operator and layer potential confused. You can see why. One of them is in the whole space. That's the one with the tilde. One of them is just on the boundary. That's the one without the tilde. So the tilde tells you where you're living. These 2 are just defined on the boundary. And then, of course, you have the whole thing, which is the space with both obstacles in it. And maybe if I have some chalk somewhere, I can draw a picture. So we just have 1 and 2. Doesn't really matter what they look like. They just have to be disjoint. Okay? So 1 has just omega 2 inside. One with just omega 1 inside. This one is filled up, and then the last one has both of them together. So you can think of it as almost measuring the difference, right? You're looking for the difference in the force between 2 objects, and so you want to think of it almost like a perturbation. Okay? So this trace formula is much more general, but we do this case so you can see what's going on today. We have s is greater than -1, and so we take the Laplacian with all the obstacles in it. We subtract off the Laplacian to some power with only 1 obstacle, with the second obstacle, and then we have the free space one. Curl is so that our space is divergence free, and we're actually looking at an electric field. So we showed that this is trace class, and it's nice again because this is really the only combination of the operators that is trace class. If you just take 1 or 2 of them, it's not trace class, you would have to use cutoffs in the boundary, and we do that also in the paper. But this is the unique combination, and the trace of this guy can be expressed in terms of the psi function. Psi of I lambda is log det, so this is the Fredholm determinant of these two layer operators acting on the boundary, and this is the real relative Casimir energy. Okay, so this takes into account the fact that you have mixed boundary conditions. What Jan Long and Alexander did was they sort of said, okay, well, you know, it looks like the functional calculus for the Laplacian, but this actually takes into consideration the fact that you have problems at lambda equals to 0, that there are mixed boundary conditions. And what's fun and annoying all at the same time is that all of the poles, and even though they're infinite rank, in the relative trace formula, they all cancel each other out. So we end up with this nice formula here, and this is explicitly computable. And so Timo and his PhD student have finished the relative trace computations based off of the function case. And so in the future, we would hope to be able to do this for the full case, for the Maxwell equation case. And why do we like this? Well, the boundary element method has been around for quite some time. And so all of these determinants here, they actually behave rather nicely numerically. And Timo was able to do some sparse calculations with Shafshu. And you can check them out too. They just appeared maybe 2 weeks ago for those of you who are joining us from the physics community. Okay. So what are the differences to the scalar case? We have curl-curl. This is present. Projection to divergence-free vectors depends really heavily on boundary conditions. I showed you some small computation at the beginning, which has a lot of vector calculus. And you can see already that just to translate the boundary conditions into something you can compute is difficult. This operator has a pole at lambda equals to 0. This pole is of infinite rank. This operator is also not compact. Therefore, we use a lot of Fredholm theory in the original paper with the Helmholtz equation. And this theory isn't available to us in the Lipschitz domain case. It's only done for C2 domains in the literature by Maitreya, and Maitreya. Some poles at 0 are gauge, and some are topological, so they involve some kind of counting of the number of loops of the domain. So if you have a torus, you would expect something different than if you had a sphere. And this adds to the study. Okay, but that was the main result, was to show that we have this trace. In some sense, it represents the pulling apart of the objects. It would be nice if we could make them move at some later time. It's represented by this formula with these layer operators that people doing numerical analysis like to use, and it represents the Casimir energy. And if you'd like to see some more things, we have a whole slew of papers here. So this paper talks about spectral theory in the exterior of objects. And the scattering matrices, I told you that these determinants also have some interpretation in terms of scattering matrices. This paper provides the relative trace formula in the function case in any dimension. It was the first example that I showed you. So the first example comes from this paper. this one is kind of out of place. It shows that you can use boundary layer theory to also represent solutions to the heat equation and do some control theory with them. I discovered that really people know a lot about integration by parts after working on this. So it's surprising, but this type of layer potential theory actually does work also for the heat equation. This relates to scattering matrices to these Fredholm determinant formulas. And this is where most of the electromagnetic scattering theory, the relative traces that I showed you, this paper is where it comes from. Okay, so proof that you can do a lot of mathematics when there is no television. So most of this was written during COVID. Okay, so since we have maybe a little bit of time, we can talk about a little bit of the proof. So if we start with lambda is greater than 0, if we wanted to prove this relative trace formula, how would you start to do it? Let's just have this in mind in case you were interested. So we take the following formula for the difference of the resolvents. This is the relative resolvent. This is the free resolvent. So even before we start with a relative trace, we can actually compute the difference just between the free and the resolvents with both obstacles in. And you can see that it's actually expressible in terms of these layer potential operators. So here you have what looks like the electric field, and then you have a nu cross, and then you have the transpose of the operator acting on the larger space applied to F. And so as it turns out, lucky for us, and lucky for people doing the Casimir effect, that a lot of the poles coming from this operator are canceled out by sort of concatenating all the operators together. So this is how you write this in terms of these electromagnetic operators. And so if you wanted to prove this, you would show that this maps functions satisfying the Helmholtz equation. And then if we start with some function, which is not a function because it's a vector field, and sorry, it shouldn't be a function, it's a vector field. We look at the difference of the free resolvent applied to curl curl of F. We look at this. We can actually write this in terms of the resolvent already because we have representation formulas for these operators. This satisfies relative boundary conditions. It's divergence free. We actually have to show that the trace of U is 0 on the boundary, and this can be easily checked. This formula is not too bad to check. But this difference actually describes the thing in question. So we do this by taking this part and this part and show that it indeed solves the correct problem. And also in part of the proof, you can see that when we expand things out and we're looking at this sum, this has some very, very sad looking and complicated formula here. And it has a genuinely infinite rank pole at lambda equals to 0. These are Maxwell eigenfunctions. These are Neumann eigenfunctions. And we can express these operators. So you can see that this is genuinely an infinite rank pole at lambda equals to 0. And that somehow magically the domains are defined so that there's a cancellation property. And when you form the difference here, after you've subtracted all of them, the poles cancel out. We checked it numerically. We were afraid at the beginning. I have to be honest. I was afraid. The poles cancel out because of the domains, and you end up getting this nice formula. So should you be really interested in the technical details of the proof, you can read them, but that's sort of the main idea of what we did over the series of papers. So I have like 10 minutes left. If you have some questions, this would be good. Everybody was very quiet during my talk, which is quite unusual. Oh, okay, because we started a little bit earlier. We had our helper who was like so fast. I was like, I got here early because I was like, oh, it'll take a while. I have a Mac. Like, where's the plugs? Like, is there a plug? Nobody knows. The next Mac will not have any plugs. We also do the computation with the cutoffs, and we have also compared the trace formula and how the force scales like the distance to the numerical experiments, and they agree. What Timo and Xiaoshu and Alexander have done, I'm not part of this numerics work, is actually considerably faster, and it is a bit more rigorous, we think. So yes, they do agree, and good news for us. Yes? Yes, okay. Okay. Okay, so what we do is we take the Stratton-Chu representation formulas, we take the restriction to the boundary. There is a thing called the voltage to current map, and this is the analog of the Dirichlet to Neumann map in the function setting. We've never seen an expansion for this map before. We expanded out in terms of a basis of Maxwell eigenfunctions and Dirichlet eigenfunctions using the Hodge decomposition. So the result is extremely general. You can have any arbitrary collection of Lipschitz domains. Remember, most of our estimates are based off the interior problem, so really you only have one. So just any Lipschitz domain. If you wanted to take a general manifold, I imagine that there would be, of course, an analog of this because you have representation theory on compact domains. And you would be able to write down a similar formula. However, for the layer potentials, it doesn't always make sense to use a general domain because you want this free space Green's function. So if you have, you want a free space Green's function. Yeah, so if you have some kind of general metric, I guess if you have a Green's function and you knew what the Green's function was explicitly, then of course you would have a lot more information if you took out an obstacle. And you can do layer theory, boundary layer theory like this. The matrices do it on very general manifolds. And I imagine that if you were just simply interested in this formula and expanding it using topological constraints, then you would be able to go further. But we do it, it's any arbitrary Lipschitz domain, and you can have a collection of them and have the inverse, and then it depends on the topological invariance, the structure of the domains. Does this answer your question? Okay. I mean, it's a bit hand-wavy, but the proof is in the paper. If you'd like to discuss later, that's fine. Well, so the Casimir energy scale is like the distance between the two obstacles, right? So if you have two flat obstacles, this distance is constant. If you have two rounded obstacles, then there's more energy between the points that are closer than the points that are further away. And this is the product of putting yourself into a specific coordinate system. The original paper by Heinrich Casimir is very short, and it's done for two thin plates. So that's why we wanted to do Lipschitz domains.